Welcome, everybody. I really do appreciate everybody coming out and joining us today. Welcome to this week's rendition of the Fall 2021 DeFord Lecture Series. As many of you know, the DeFord Lecture Series, which used to be called Technical Sessions, has been a tradition in the Department of Geology here at the Jackson School since the late 1940s, long before there was a Jackson School. And it's been our official venue for disseminating research from graduate students, from faculty, and from distinguished researchers from around the country and around the world. And today we're very happy to have Claire Masteller joining us in that capacity. The DeFord Lecture Series was named after Ronald DeFord, who joined the university as a professor in 1948. And was a graduate advisor in the department from 1949 to 1967. He also advised a very large number of students during his time in the department. And one of his contributions, he was very active in developing and leading technical sessions. And so in honor of his contributions, Technical Sessions was renamed to the DeFord Lecture Series a couple of years ago. And continuing in the tradition of having outstanding researchers present their most exciting recent results, we have Claire Masteller joining us today. And to tell us a little bit more about Claire is Joel Johnson. Thank you.
Hello, everyone. Thank you for being here. And it is my pleasure to introduce Dr. Masteller. So Claire went to the University of Pennsylvania as an undergraduate and did research with Doug Jeromack there, then went to do a PhD at UC Santa Cruz with Noah Finnegan, and did a postdoc at the GFZ Potsdam. And I always have to look up exactly what it translates as, the German Research Center for Geosciences with Niels Hovius. And without further ado, Claire will tell us about the research that she is doing now. So take it away, Claire. And actually, I don't think we said anything about questions. Sorry, psych, I caught you. Put your questions in the question and answer, and in general, they will be asked after the talk. Go for it.
All right, thanks, Joel. So hi, everybody, and thank you so much for the invite to come and talk to you today. And so today I'm going to talk about how gravel bed rivers have a memory of the past flows that run through them. And much of this work was done in collaboration with Joel, hence the nice orange highlight around his name. So let's get into it. So rivers dissect landscapes all across Earth, and they act as the main conduits that are moving water and sediment across Earth's surface. And so we generally observe that the shape of a river reflects some balance between local climate, hydrology, and that transfer of sediment through erosion and deposition. But we typically think about the expression of those variables over fairly long timescales, with a lot of our focus being on the channel long profile. But over shorter timescales, our landscapes and our rivers are consistently exposed to unsteady environmental forcing or the weather. So if we consider rain falling on a catchment like this one, we know that this rain is going to be concentrated into discrete storm events. And during those storm events, once our rain hits the landscape, water will be routed across its surface until it finds its way into our river channels, which leads to time variable discharge or flooding. And so during those discrete flood events, sediment will also move through our landscape. And it's that movement of sediment that will cause the landscape to change its form. And so that erosion and deposition is ultimately what's integrating that signal of rainfall onto Earth's surface. So this sediment transport part of the feedback is fundamental to understand how climate might imprint itself onto the shape of the landscape. And so this places a key constraint on this coupling between climate and landscapes. And that constraint is that sediment must move. If sediment doesn't move, our landscape won't change, and as such might not hold any evidence of a past rainfall event. And so even despite this unsteady forcing, we do observe that in general, alluvial channels will widen until they reach a stable condition where the bankful discharge will just exceed the threshold for motion, or the point where sediment will start to move on our riverbeds. So our channels, as they're shaped, are often poised to transport sediment. And so this stable condition is commonly referred to as threshold channel theory, and I'll be using that term throughout the rest of the talk. And so in aggregate, if we look at many rivers of many sizes, threshold channel theory appears to describe this stable river channel geometry quite remarkably. So we can see the scaling relationship between discharge and channel width holds over about 14 orders of magnitude in discharge, and it holds both across rivers that were formed in a lab and across rivers across Earth's surface in the field. But this threshold channel theory only predicts that stable condition for alluvial channel geometry. What it doesn't do is it doesn't prescribe or predict the pace or the path that a channel might take to adjust in response to a change in hydrologic conditions. So a change in discharge or a change in climate. And so essentially we don't have a great idea of what will happen at a point like this, where we fall off of our line or our stability condition. And so we're not sure what might happen to a channel if it gets here, or whether or not it can actually physically occupy this space, or if there are a series of internal feedbacks in our rivers that keep our points much closer to this stable criterion. And so we're interested in interrogating this idea because we know that our river flows are changing as our climate continues to change. And so what I'm showing here is a data compilation from Louise Slater and Villarini, and this measures changes in flood magnitude and frequency across the United States from 1965 to 2015. And what's important to note is that both the magnitude and frequency of floods is increasing or decreasing depending on where you are in the US. And the strength of those increases and decreases is also quite variable. So given these observations, it's not only clear that there's not a one-size-fits-all channel response that we might expect in the future, but also that these channels are likely currently being pushed out of their stable conditions, and they're going to have to adjust to these new flow regimes as our climate continues to change. And so we're interested in understanding what might set the pace and the scale of the adjustment that we'll see in our channels as we go into the future. And so to start to think about that question, we're going to return to that key requirement for integrating a climate signal into a landscape, that requirement that sediment has to move. So our river flows must exceed the threshold for motion in order for our channels to adjust. So we can, in simple terms, represent the onset of particle motion as that balance between driving stresses and resisting stresses that act on any individual particle. Once those driving stresses win out, the particle will start to move, sediment transport begins. So we typically refer to that threshold for motion as a critical shear stress, or a non-dimensional quantity called critical shield stress, which you'll see appear many times in this talk with the variable name tau star C, right, which you can also see right here. And so in most fluvial erosion models, we assume that this threshold or critical shear stress is constant. And so on this idealized hydrograph, we represent that constant threshold as a sharp straight line. And so below this line, our erosion models would never predict transport to occur, and there's relatively little water in the channel. Above this line, our erosion models would always predict transport to occur, and the higher the threshold is, the larger the flood we would need to begin to move sediment. And so a consequence of this assumption of a constant threshold for motion is that our erosion models have no memory. So our predictions of sediment transport at any given time don't consider the state of the channel at any previous time step. Instead, sediment flux is just going to be predicted as a function of how far above this line we are. But previous studies have shown that the threshold for motion is not actually constant. And in some cases, it can vary in time with some structure. And that variation in time implies that there is some memory in our system. So Reed et al. 1985 was the first to note this memory effect. And what they observed was that the threshold for motion in a gravel stream was sensitive to the time between storm events, such that for a longer time between storms, our threshold for motion increased, which essentially raises this line on our conceptual hydrograph. And so that increase in threshold then requires a larger flood to move sediment. And so after these longer waiting times or these longer times between storms, our channel ultimately becomes more stable. Something else that's quite interesting to point out here is that in our common form of our erosion models, we would predict that during these in-between times, these times between our floods, that absolutely nothing is happening on our channel bed in terms of transport. Yet, after longer in-between times, we see this increase in bed resistance, implying that indeed something is changing on the channel bed, even when we're not observing or predicting active sediment transport to occur. And it's worth pointing out here that this observation by Reed isn't all that unique. So at the event scale, we often observe something similar called in a hysteresis in our sediment flux measurements, where we typically see a reduction in sediment transport on the falling limbs of our hydrographs, implying an increase in threshold during individual flood events. Like Reed, we've also seen in flume experiments that our bedload transport rates are reduced with increasing time between storms, again, implying an increase in threshold across transport events or between transport events. And even over a season, folks have observed a reduction in sediment transport rates as we move later into the season, implying again that our bed is getting stronger and our threshold is increasing. So then the natural question is, well, how does the threshold increase? What are the processes behind this observed strengthening of the bed? And so to interrogate this idea, we did a set of flume experiments during my PhD. And what we found is that during these low flow times, so the times where we would predict that nothing is happening on the bed isn't actually frozen in place. Instead, what we see is that we see the grains on our bed are wiggling in their pockets. And that subtle wiggling allows for a local reorganization of our bed surface. And what we observed is that that wiggling ultimately led to a reduction in the number of high protruding particles on our channel beds. And we found that the number of those high protruding particles, which are the least stable particles of our bed, are the ones that ultimately drive our sediment transport rates. So this decrease in surface roughness, just by grains simply wiggling or falling into nearby pockets, even though it's subtle, leads to almost an order of magnitude reduction in sediment flux for a constant flood size, which essentially means that we can really measurably change our threshold just by wiggling these grains around a bit. On the flip side of the coin, sediment transport events, which happen during our floods, can actually restore that population of highest protruding particles, which you can see on the figure on the left for my experiments, where these percent changes are the number of particles that sit at any of these elevations on the bed. And during our inter-event flows or our time between storms, we see that we get this reduction in highest protruding particles, which is associated with an increase in threshold. But then following transport events, we get a restoration of that high protruding population, which essentially acts to reduce the frictional resistance between grains and again, reduce our threshold back down. So we're getting a really dynamic response in threshold due to these subtle changes in simply the number of grains that stick up really high above the mean elevation of our bed. And so what we see is that our threshold for motion is ultimately going to be set by this competition between the stabilizing effects that happen under low flow and build order on our bed via local grain rearrangement, and the destabilizing effects that occur during sediment transport events and floods that ultimately disrupt that order that's been built on the bed and then act to reduce the threshold for motion again. And so now we want to go see if we can see similar patterns in variable tau star C or variations in threshold in a real river system. And so to do this, we're going to jump to the field and go to Switzerland. And I'm going to talk about 19 years of critical shear stress measurements from a river called the Erlenbach, which is in the Swiss Prealps. And so this data set from the Erlenbach is an incredibly unique data set because this channel is actually one of the most well-monitored mountain streams in the world, with over 3 decades of continuous bedload transport measurements. And those measurements are made by geophones that are installed in the channel bed that measure individual impacts of bedload particles as they pass over those plates. And using those impacts, we can identify directly the onset of sediment transport and the threshold for motion for every transport event over our 19-year record, which gives us about 500 measurements of threshold to work with. And so using that data set, we can see that the threshold for motion or critical shear stress varies by an order of magnitude in this channel, which reinforces this idea that the assumption of a constant threshold for motion doesn't quite capture the full complexity of sediment transport in real gravel bed rivers. And so we can plot this same data as a time series. And what we see is that that wide variation in the threshold for motion is also not random. So here I'm plotting 3 years of critical shear stress measurements from the Erlenbach. And what you can see is that the threshold for motion increases through each year, then appears to be reset in the winter and then increases again. And it's worth pointing out here that we see this pattern of increasing critical shear stress across 11 of the 19 years on our record. So, which highlights that the patterns in the evolution of the threshold for motion at the Erlenbach varies both in a significant fashion, but also in a fairly systematic fashion. So now we want to take that data set and explore the effects of prior flows on setting that threshold for motion. So on this first plot, I'm going to plot the mean low flow stress on our x-axis. And then on the y-axis, I'll plot the threshold for motion that's measured during the following transport event. And so for our lowest inter-event flows at the Erlenbach, we see no correlation between the threshold for motion or critical shear stress and prior low flow magnitude. So these flows don't appear to contribute to any of that history dependence that we see at the Erlenbach. But this makes sense when you go look at the channel, because this is what the channel looks like during one of those flows. There's just not enough water in the channel to submerge the bed to do much reworking of grains or wiggling of grains into more stable configurations. So it's no surprise that for these very low flows, we don't see much of a signature of those flows in our threshold data. If we look at the upper range of our inter-event flows, our critical shear stress is well correlated with that prior flow magnitude, such that a larger inter-event flow is resulting in an increased threshold for motion. And so this suggests that the bed has actually integrated the effects of that inter-event flow. And if we look at images of the bed during flows of this size, we can see that most of the channel is submerged in water, which makes the local reworking that is necessary to adjust our threshold more likely. But because the threshold for motion at the Erlenbach varies, for this range of flows, we also have events where sediment transport can sometimes occur, depending on what our threshold is for a prior event. So we're also going to look at the effects of our transporting flows both in this same range and then for flows that exceed this range separately. So on this plot, I'm going to plot the previous peak transporting stress on our x-axis. And again, on the y-axis, I'll plot the critical shear stress of the following event. So again, for this intermediate range of shear stresses, we see a similar dependence of the threshold for motion on prior flow magnitude, such that with an increased flow magnitude, we get an increase in the threshold for motion. So this suggests that even though we have measurable transport going on in our bed, the local reorganization is what rules the day here in terms of setting our thresholds. Finally, we can look at our highest discharge transport events. And these are events during which transport is always observed to occur at the Erlenbach. And for these largest flows, the threshold for motion is independent of prior flow. So there's an apparent loss of memory that's built during any of our intermediate flows, suggesting that we're really introducing a lot of disorder through transport during these conditions. And so this is a picture of what the river actually looks like during one of these highest flows. As you can see, it's pretty intense. So flows like this have the ability to move boulders and cause landslides and break up any steps that have been built in the bed. And so they're really good at disrupting any of the order that we might have built during our more intermediate sized flows. So similar to our experiments, we see this competition between these stabilizing effects that occur during low flows and these destabilizing or weakening effects that occur during high flows that contribute to some change in threshold or evolution of threshold through time. And so we can start thinking about how the threshold might change as a consequence of which of these two processes is ultimately dominating on the bed. And so given these observations, Joel and I have taken a crack at building a state function to describe how the threshold will evolve as a function of these magnitude dependent strengthening and weakening effects. And so we can write an equation to represent the change in threshold at any time as a competition between strengthening processes and weakening processes. And so here, the main driver of this equation is going to be the strength of the flow, tau star, relative to some threshold value, tau star C, which is allowed to change in time. And so here, the memory in this model is embedded in this part of our function because it includes the threshold, which again, we allow to change through time. So even if we have the same discharge, we may get a different weighting of strengthening and weakening effects based on what our tau star C is. And so this is a new twist on Joel's 2016 paper that was published in eSurf that takes a similar approach, but instead of thinking about this or driving the model through flow magnitude effects, it considers net erosion or deposition. And so this is really sort of the precursor to the work that I'm presenting today. And so here again, our equation has two main components representing that competition between strengthening and weakening processes, where following our field and flume observations, weakening only gets turned on when the threshold for motion is exceeded or when sediment transport would be predicted to occur. And our model ends up having 4 free parameters, so 2 coefficients and 2 exponents that act to weight the relative efficacy of strengthening and weakening processes independent of one another. The model also has a feedback term called B, which accounts for the fact that there are physical limits to the range of conditions that a riverbed could possibly explore. So the riverbed can only be so loosely or tightly packed. So the stronger the riverbed already is, the harder it will be for the riverbed to get any stronger. The weaker the riverbed already is, the harder it will be for the riverbed to get any weaker. And so this B parameter essentially captures how close we are to those physical limits in our system. And then it scales the strengthening and weakening behavior accordingly. And so here's a toy example just to illustrate how the model will behave in response to a repeated synthetic hydrograph with a peak flow about 2 times our starting threshold. And so here the flow that we use to drive the model is in the top panel in blue. And then our calculated threshold is this pink line here. And the individual components of our model, our strengthening and weakening effects, appear in teal and orange in this bottom plot, black being the combination of the two. And so what you can see here is that through this synthetic model run, our stabilizing processes dominate, but those stabilizing or strengthening processes dominate with diminishing returns as our threshold evolves or as we approach the maximum, as our threshold evolves or as our bed gets stronger because we are starting to approach the maximum physical limit of our bed. And so with this repeated hydrograph, what you can see is that we do turn on weakening when the flow exceeds our threshold in our early models or in our early events. But as our threshold continues to increase, we reduce the impacts of weakening until we essentially turn it off by the 3rd event. And which means that essentially by raising the threshold like this, we're shutting off sediment transport in the system, which means that ultimately our channel will no longer be able to change its shape because it can't move mass around. And so we're going to take this model now out for a test drive using the Erlenbach data that I presented earlier. And we're going to run a whole suite of models across a wide range of our parameter space and see how well the model is able to reproduce our observations of time variable threshold. And so to do this, we ran a lot of models, but what we do is we drive the model with a time series of flow at the Erlenbach, and then we'll compare model performance to our time series of threshold. And we're gonna look at 23 different years of critical shear stress measurements to do this. And what we find when we do this is that the mean absolute error of our annually calibrated state function, so the best fit or the best performing model from every year, performs better or better matches our observations than the error that we would get if we compare those observations to an assumed constant tau star C. So we can also look at model performance with average parameters across all years, and those do a bit worse, particularly in years where we see large weakening events. But generally, in the majority of cases, our state function outperforms a constant assumption of tau star C quite well. And so here is what some of our best performing models look like for a range of different scenarios. Here we have the flow time series that's driving the model in blue in the top panel, and then the model predicted evolution of threshold in the black solid line with our field measurements as the black dots here. And what you can see for an instance or a year that did not have many large floods, strengthening dominates the entire time. We don't see any weakening, and we can capture that increase in threshold where we see some diminishing returns through the year. We can then look at a scenario where we have a large flood early in the season. What we see here is that the model predicts a fairly large drop in the threshold for motion, and then a recovery or a re-strengthening of the bed in response to these more moderate events. Again, matching our data and observations very well. Here we can look at a flood of a similar size that occurs later in the season. What we can see here is that the model predicts strengthening or an increase in threshold up until this large flood event where we do predict some weakening, but that weakening is muted relative to our early season flood, potentially because the bed has already stabilized quite a bit. And then we can, in our final case here, we can see multiple fairly large floods that occur throughout the year where the model captures a weakening event and then another weakening event, leading to an overall decrease in the threshold for motion through time. So across all of these different scenarios, our model is able to capture the trends that we see in our threshold data quite well. So even though we're only driving the model with our discharge time series, it does do a pretty great job. Though I will be the first to admit that our model also is not perfect, though its performance is quite encouraging. So based on the structure of the model, we're only driving it with discharge. So it's not going to do a great job capturing any events that might influence threshold that are uncoupled from discharge variability. So like something like this, a landslide. So this is captured by Antonius Gali, who is a PhD student at GFC Potsdam. And what you can see is that the hill slope essentially falls into the river here, something that our model would never be able to capture, but certainly introduces a significant amount of disorder into the system that stands to potentially influence threshold. And so while our model can take into account the flow history effects that might inform threshold evolution, that it can't capture more complicated or discrete events like this. That said, it does still do a pretty good job. Oh, and it's going to play again. And so now we're interested in seeing how transferable the behavior, so this competition of strengthening and weakening behavior that we see at the Erlenbach might be to other systems. And so we've also been able to get our hands on impact plate data similar to what we have at the Erlenbach for 2 proglacial streams in Austria. So we can compare the threshold time series in these 2 proglacial streams to the time series and threshold driven at the Erlenbach, where the hydrology is more storm driven. And so what we can see is that we have our threshold measurements in blue and in red, respectively, for our Austrian proglacial streams, and then our time series of thresholds in the Erlenbach in yellow. And what you can see is that there is some structure to how threshold is evolving in our proglacial system settings, where we have low thresholds at the beginning of the year that increase through the year, and then at the sort of height of summer start to drop back down or decrease later in the season. And so we get, again, a wide range of thresholds, but the temporal pattern that we're seeing is fairly distinct from that repeated strengthening that we see at the Erlenbach. And so we can look at the range of threshold that we're getting in each of these cases. And we see a much wider range of thresholds at the Erlenbach than we see in our proglacial streams, but we do still see quite a bit of variability there. What's really interesting and encouraging is when we standardize these distributions, they all collapse onto one another quite well in a relatively normal distribution. So that's a really encouraging result that we are getting similar behavior, similar variability and threshold across these different hydroclimates. We can also, again, do this comparison between the peak transporting flow of our previous event and then our next measured threshold for all 3 settings and standardize that data. And what we see is that we see for these more intermediate flows again, that threshold goes up in all these settings. And then there's a rollover point to weakening that's fairly consistent across all 3 data sets. And this is really exciting because even though we have very different structures in terms of our time series, and we have systems that are being driven by very different flows, we get really similar dependence or flow magnitude dependence across all of these systems, which means that the model that worked fairly well at the Erlenbach might also be able to capture very different temporal variability in a proglacial stream or in another setting. And so I'm really excited about this result. And so if we go back to thinking about how threshold or that requirement of sediment moving, or that key requirement of sediment moving and how that relates to what our channel looks like, how wide our channel is, we can start thinking about what threshold across this wide range of thresholds does our bank fold width actually reflect? And so we can go to the Erlenbach and plot the shear stress for bank full on our plot here. And what we see is that the bank full geometry at the Erlenbach actually appears to correspond to our maximum observed threshold. So it looks like our river evolves, or our river cross-section is evolving to reflect the strongest state that our river sees through time, which is really interesting. And so given that, we're now moving towards connecting this variable threshold to changes in channel width that we can measure. So we're trying to now, in work that I'm doing in collaboration with Colin Phillips, think about fine scale variability in channel width and whether or not we can use that to invert for spatially variable thresholds that give us some insight into how sensitive our river channels might be to changing flows. And so here we've extracted channel width, I believe every 100 meters across this 75-kilometer test section of the Eel River, and looked at how the width that we measure diverges from what we would predict from the discharge width scaling that I showed you earlier. And what you can see is that we have these sustained sort of diversions from this predicted width discharge scaling that might indicate that we have thresholds that are maybe taking up some of the slack here. And so we hope to move towards looking at how threshold might vary spatially in this system and how that connects to our stability criterion of channel width. We're also starting to think about how to connect changes in threshold and changes in channel width through time, and think about how what portion of a disturbance or a large flood changes in threshold could take up relative to an adjustment in channel width itself. So we have two cases here, one from the Eel River and one from the Colorado Front Range, where we have different types of perturbations. And those different types of perturbations lead to very different responses in changes of channel width, which we expect to be related again to changes in threshold. Here, potentially, if we can maintain a stationary channel width, our threshold is maybe taking up more of the slack in terms of adjustment in response to unsteady conditions. In a case where we have really large and measurable changes in channel width, potentially our threshold response is really muted, and that dynamic adjustment is almost entirely taken up by the width response. So how those two things interact through time and in response to different perturbations is something that we're really interested in exploring going forward. And so if we think about these knock-on consequences of a variable threshold for motion, we start with a changing hydroclimate. That changing hydroclimate can, or variability in flood frequency, variability in flood magnitude can modify our erosion thresholds. As we modify those erosion thresholds, we essentially determine when and under what conditions the channel can change. So depending on how much our erosion thresholds change, we can potentially buffer or amplify channel response in things like channel width in response to this changing hydroclimate. And so we're really interested going forward in thinking about how these dynamic erosion thresholds might influence the sensitivity of our river systems in response to climate change. And so to wrap up here, we've looked at how inter-event flows or times between storms are actually able to modify the stability of gravel bed rivers, something that our more commonly used erosion models don't account for. And we showed that those dynamic changes in threshold are due in part to variations in bed roughness as the bed adjusts to prior flows. We've also shown that the threshold for motion is dependent on both prior flow duration and prior flow magnitude, and have implemented a state function to better describe that evolution in bed mobility in response to variable flows. And through application of that model, the Erlenbach have shown that this state function and flow history model approach has potential to be widely applicable because the flow magnitude dependence that we see seems to hold across a range of different settings. And so going forward, we're really interested in continuing to explore what is actually setting the physical limits of thresholds in a river. So why are thresholds less variable in the proglacial streams we looked at than we saw in the Erlenbach? And then what are the constraints that threshold channel theory and with adjustments place on how much our thresholds can evolve and vice versa? And then what degree of flow variability is our channel bed actually able to absorb before we can get measurable changes in channel shape? And then what types of signals then, given all that, might actually push the channel to a new equilibrium state rather than be buffered out? So in general, we're just nibbling on all of these questions to get at this much larger question of how sensitive are gravel bed rivers ultimately to a changing hydroclimate. So I will leave you with that question that we'll be thinking about for at least the next couple of years and take questions. But thank you so much for your attention.
Yeah.
Thank you very much.
Yes, thank you very much, Claire. So
it's clear, we got a lot of questions, that you really stimulated a lot of discussion and a very interesting talk. I just want to throw out, given that, this response of, stream beds to, potentially changes in hydrologic processes as a result of climate change, it's nice that Joel has sort of linked us into climate change by having the Henrik Averkamp painting in the background there, a
Yes.
nice illustration of the Little Ice Age in the Dutch painters. So I just had to get that in there. It's like, wait, I know that picture. It's Averkamp.
Thank you for noticing. So yes.
But yes, but very, very interesting talk. I really do appreciate it. And again, thank you everybody for coming out. And Claire, thank you for really a very interesting talk. And that's it for this week. And we'll see everybody back here next Thursday. Thank you very much.